All right, so we're diving into geochemistry today.
Awesome.
We've got a ton of info here from Wikipedia,
Great.
and we're going to extract the coolest stuff for you.
Sounds good.
Geochemistry. Think about it as like Earth's giant chemistry set,
Yeah.
but instead of beakers and test tubes, we're talking about the entire planet. You know, a crust, the oceans,
Right.
even other planets. And as a chemistry student, this is a field you're really going to want to dig into.
Oh, absolutely. It helps us understand how our planet formed, how mountains rise and erode,
Wow.
and even how life itself evolved.
That's incredible.
It's a field with huge scope.
Okay, so let's break it down starting with the basics. Geochemistry boils down to the chemical elements
Yeah.
that make up everything.
Yeah.
It's like the periodic table come to life.
I like that.
Each element has an atomic number, right?
Right.
Which tells us the number of protons in its nucleus.
Exactly.
But then we've got isotopes. These are like different versions of the same element.
Okay.
Same number of protons, but with a different number of neutrons.
A perfect example is chlorine.
Okay.
I've got chlorine-35 and chlorine-37.
Okay.
Both are chlorine because they have 17 protons,
Right.
but the neutron count's different.
So they're not just like a scientific curiosity, right?
Yeah.
What can we do with isotopes?
Well, these isotopes are powerful tools for geochemists.
Okay.
Stable isotopes act like tracers. We can follow chemical pathways and reactions.
Oh.
And radioactive isotopes are like nature's clocks. We can date rocks and other materials.
Wow.
We can figure out how old a rock is just by using its isotopes.
It's like having a time machine.
Exactly.
That's so cool. Now, when we talk about how Earth got its unique chemical composition, there are two key processes, differentiation and mixing.
Yeah, it's like separating ingredients and then blending them in a specific recipe.
Right.
A really good example of differentiation is the formation of basalt at mid-ocean ridges.
Okay.
As the Earth's mantle partially melts, some materials, the ones that are more resistant to melting,
Okay.
we call those refractory.
Got it.
Those stay behind.
Okay.
And the rest of that melt rises up and solidifies to form basalt.
Interesting.
And this separates the elements based on their chemical behavior.
So it's like Earth has been sorting itself out over millions of years.
Yeah.
But this differentiation isn't just happening deep inside Earth, right? We see it in everyday things, too.
Oh, for sure. Absolutely. Think about granite.
Yeah.
It's a very common rock. When it's exposed to the elements, it erodes,
Right.
breaks down into different components. Clay sandstone dissolved minerals.
Wow.
And each of those is carried away by a different process.
Okay.
That's differentiation in action, driven by weathering and erosion.
So erosion's like nature's way of separating a rock into its ingredients.
Yeah, I like that.
Now, how about mixing? How does that come into play in this giant chemical dance? It sounds like it would kind of undo differentiation.
It does. It's about bringing those separated materials back together.
Okay.
It happens through a lot of processes. Think about plate tectonics,
Right.
where those oceanic plates dive back into the mantle, carrying their differentiated materials with them,
Right.
or through melting and re-solidifying rocks during metamorphism.
So it's this constant cycle
Yeah.
of separating and recombining that drives the evolution of our planet chemically.
It really is a continuous cycle.
Fascinating how dynamic Earth's systems are. Makes you realize that even solid rock is part of this constant change.
Yeah.
But let's zoom in on Earth's crust, the ground beneath our feet.
Yeah.
What's the chemical story there?
So Earth's crust is mostly made up of oxides.
Okay.
These are compounds where oxygens combine with other elements.
Okay.
And get this, oxygen makes up almost half of Earth's crust by weight.
Wow, oxygen really is everywhere.
Yeah.
So besides oxygen, what are the other big players in the crust?
Silica is a key player.
Okay.
Silicon dioxide. Think of it like an acid in the Earth's crust.
Okay.
It reacts with other oxides to form silicates,
Right.
which are the most common minerals in igneous rocks.
And those are the ones formed from cooling magma.
Exactly.
So silica is like the master chef of the crust,
I like that.
combining different oxides to make all these different mineral dishes.
Yeah. A perfect analogy.
And while silicates are like the stars of the show,
Right.
we also have non-silicate minerals,
Yeah.
like carbonates, oxides, and sulfides.
Exactly.
They may only make up about 8% of the crust,
Right.
but they're still important in all sorts of geological processes.
Oh, absolutely.
Speaking of igneous rocks, we always hear about different types, granite, basalt, and so on. Does geochemistry help us understand these differences?
Absolutely. Igneous rocks are classified based on their silica content.
Okay.
The ones with high silica content are called felsic rocks,
Okay.
like granite.
Got it.
Low silica rocks are called mafic rocks,
Okay.
like basalt.
Right.
And then we have the ones in between called intermediate rocks.
So it's like a spectrum from high silica to low silica,
Exactly.
with each rock type having its own chemical fingerprint.
It's a very elegant classification system.
It is. And just to make things more interesting,
Oh, yeah.
there are also alkali or soda rocks,
Right.
which are rich in sodium and contain unusual minerals like nepheline and lucite.
Yeah, they're like the outliers,
Right.
showing us just how diverse Earth's chemical kitchen can be.
It's amazing how each layer we peel back in geochemistry just reveals more complexity,
I know.
which is what makes it so fascinating.
Yeah, definitely.
Yeah, it really is.
Okay.
It makes you appreciate just how complex and amazing our planet is.
Right.
Now let's switch gears from solid rock to the oceans.
Yeah.
What role does geochemistry play in this massive watery world?
The oceans are like a giant chemical playground.
Oh, yeah.
Even though they're only found in super tiny amounts, trace metals have a big impact on the chemistry and biology of the ocean.
Okay.
Metals like iron, copper, zinc,
Right.
they interact with the major ions in seawater and form complexes.
So it's like these trace metals are teaming up with the more abundant ions and changing how they behave.
Exactly. And their behavior isn't static either. The chemical form of these metals is what we call their speciation. It changes depending on whether the ocean environment has a lot of oxygen or not.
Okay.
And this can affect how soluble they are, how available they are to marine organisms, and even how toxic they could be.
That makes sense.
Yeah.
So if a metal is tied up in a complex, it might not be as easy for marine life to use, right?
Exactly. And changes in oxygen levels can shift the balance of the different metal species, making some more bioavailable and others less so.
How do geochemists even study these trace metals and all their interactions in such a vast and complex system?
One way is to analyze sediment cores.
Okay.
These cores are like a history book of the ocean's chemistry.
Wow.
They reveal how trace metal concentrations have changed over time.
That's amazing. So it's like reading the ocean's diary,
Yeah, I like that.
with each layer of sediment telling a story about its chemical past.
Exactly. And this diary also tells us that trace metals aren't evenly spread out throughout the ocean.
Okay.
They have different distribution patterns that are affected by things like biological uptake, chemical reactions, and even physical processes like ocean currents.
So it's not just a uniform soup of trace metals.
Yep.
There's structure and variation in their distribution.
Exactly.
It's really cool how all these different fields like chemistry, biology, and geology are all connected.
Absolutely. And geochemists have identified 3 main types of distribution patterns for trace metals in the ocean.
Okay, what are they?
Conservative nutrient type and scavenged type distributions.
All right, let's break those down. What makes a distribution conservative?
Okay, conservative trace metals like molybdenum
Okay.
have high concentrations compared to how much they're used biologically.
Okay.
They don't really interact much with particles in the water
Right.
and tend to stay dissolved,
Okay.
which gives them a pretty uniform vertical profile in the ocean.
Right.
And their residence times,
Yeah.
meaning the average time they hang out in the ocean,
Right.
can be incredibly long, sometimes millions of years.
Wow, so they're like the ocean's long-term residents,
Exactly.
just cruising around in the water for eons. What about nutrient-type distributions? They sound like they're connected to life in the ocean.
You got it. Nutrient-type trace metals like zinc are essential for marine life,
Okay.
especially phytoplankton. Those tiny plants that are like the base of the ocean's food web.
Right.
These metals are taken up by phytoplankton near the surface,
Okay.
which makes their concentrations lower in those areas.
Got it.
And then as the phytoplankton die and sink,
Mm-hmm.
the metals are released back into the water at deeper depths.
Interesting. So it's this constant back and forth
Yeah,
between the phytoplankton and the trace metals that shapes how they're spread out in the water column.
absolutely.
Yeah.
And lastly, we have the scavenged type metals, what sets them apart.
Okay.
Scavenged type trace metals like aluminum love to attach to particles in the water.
Okay.
They bind to those particles and sink pretty quickly.
Okay.
So they have shorter residence times and higher concentrations near the ocean floor
Right.
or near sources like hydrothermal vents and rivers.
So unlike the conservative types, they're more like temporary visitors,
Yeah,
quickly latching onto particles and getting carried away from the surface.
exactly. It's amazing how these different behaviors create such distinct patterns.
It is. Thinking back to our discussion about speciation, I have a question.
Okay.
How do you think the formation of complexes and things like oxygen availability might affect how much of these trace metals are actually available to marine organisms?
That's a great question. If a metal is really tightly bound in a complex,
Yeah.
it might be harder for organisms to access it.
Right.
And changes in oxygen levels could shift the balance of different metal species,
Right.
potentially making some more bioavailable and others less.
This could have big consequences for the whole marine ecosystem.
Exactly. The bioavailability of trace metals is a complex interplay of chemical, biological, and physical factors.
Wow.
And understanding this interplay is crucial to understanding the health and productivity of our oceans.
We've covered a lot of ground in this deep dive into geochemistry. From the basic building blocks of elements and isotopes to the complex world of trace metals in the ocean.
Oh, yeah.
It's clear that geochemistry is so important for understanding our planet.
It is.
From the rocks beneath our feet to the vastness of the sea. Yeah, it really shows how everything is connected on Earth, you know. As a chemistry student, I can see how geochemistry helps us understand all those connections.
It does. And it's really cool how all these chemical processes like mineral formation or those trace metal interactions in the oceans are all linked together. Understanding geochemistry helps us see Earth as this giant, complex system where even tiny changes can have these huge ripple effects across the whole planet.
It's a delicate balance, and chemistry is right at the heart of it. And that's the beauty of these deep dives. It's not just about memorizing facts. It's about understanding the big picture and realizing how much more there is to learn.
Exactly. As you keep going with your chemistry studies, you'll find that geochemistry gives you a really tangible way to apply those core principles to understanding the world around us. It's a field that's just bursting with opportunities for discovery and innovation.
So true. So here's a final thought for you. Imagine being able to analyze the chemical composition of a simple rock sample and unlock its entire history, the forces that shaped it, the environments it's been exposed to, even hints of past life hidden in its structure. That's the power of geochemistry, uncovering the secrets buried within Earth's chemical tapestry. So keep exploring, keep asking questions, and who knows what amazing discoveries you might make.